In this video, we're going to talk about reaction mechanisms. So previously, we defined chemical kinetics as the area of chemistry where we look at reaction rates and where we look at the sequence of steps by which reactions occur. So we've talked about in previous videos reaction rates. In this video, we're going to talk about the sequence of steps that we go through for our reaction to occur. And we're going to look at how we write rate laws for those individual steps. So reaction mechanism, which is what we're going to look at here, is the sequence of reaction steps that shows us how we get from reactants to products. Often we look at just the reactants and the products, but sometimes it actually takes us more than one step to get there. So we're looking at the overall reaction, but in reality, there's a reaction mechanism. There are what we call elementary reactions, which are single steps, and we may have multiple elementary reactions that actually make up the overall reaction. So an elementary reaction deals with an individual step. The overall reaction is the summation that gives us the reaction stoichiometry. That's often what we're looking at. So we look at these overall reactions to give us a summation, but oftentimes that doesn't really tell us the steps to get from the reactants to the products. So for example, if we look at something like NO2 plus CO, that gives us, as our products, NO plus CO2. But the reaction doesn't actually go in those steps. It can't go straight from NO2 and the carbon monoxide to nitrogen monoxide and carbon dioxide. It doesn't work like that. What actually happens, or what we think happens based on experimental evidence, is that our nitrogen dioxide breaks down into nitrogen monoxide and nitrogen trioxide, and the nitrogen trioxide reacts with carbon monoxide to give us nitrogen dioxide and carbon dioxide. So the nitrogen dioxide is one of our reactants, so we can go back and keep the cycle going. So these first two steps are elementary reactions. They're single steps in this reaction. Our final reaction down here is our overall reaction. So if we look at our reaction and you think back to Hess's law, we have NO2 that shows up as on the reactant side of our first reactant and on the product side of our second reaction. So we can cancel that out. And we also have NO3 that shows up on the product side of one reaction and the reactant side of the other reaction. So we can cancel that out. So if we add those together, that would give us our overall reaction. So this slide here is a visual reaction of a visual picture of what we just said in the last slide. So our nitrogen dioxide reacts to our nitrogen monoxide and nitrogen trioxide. Our nitrogen trioxide then reacts to carbon monoxide to give us nitrogen dioxide and the carbon dioxide. So if you take a look at your elementary reactions, in the first one, we get nitrogen trioxide as a product that is immediately consumed as a reactant in the next step. We call that a reactive intermediate. A reactive intermediate is formed in one step and then consumed in a subsequent step. So anytime you have something that was not one of your original reactants that's formed as a product, and then it's consumed in a later step so that it does not appear in the overall reaction, that is a reactive intermediate. We can classify elementary reactions based on the number of molecules, or in some cases atoms, on our reactant side. something that only has one reactant is said to be unimolecular. So uni is the prefix for one here. So one reactant, unimolecular. Something that has two reactants is bimolecular. And something that has three reactants is termolecular. So we talked about for rate laws that you have to determine the rate orders from experimental evidence. However, for elementary reactions, this is the one time that we can take the rate orders directly from the reaction. The rate law for an elementary reaction actually comes directly from its molecularity because it's an individual event. So if we're dealing with an overall reaction, we have to look at experimental values. We can't determine it from the reaction. However, for an elementary reaction, we can take this directly from the stoichiometry of the reaction. So the rate law for this, rate is equal to K times O3. O3 has a coefficient of 1, so this has a rate order of 1. Same thing for a bimolecular. Same thing for a termolecular. And you will notice that the oxygen appears twice. So if we condense this down, we would have 2O as gas plus M as a gas yields O2 plus M. And notice that we have a coefficient of 2 here. So this only works for elementary reactions. I want to stress that point that you can only use the coefficients as the rate orders if you have an elementary reaction, never for an overall reaction. So this gives you some examples of rate laws for different molecularities. If things are unimolecular, if things are bimolecular or termolecular, and you can see the rate laws follow from the elementary reactions. Now, when we're trying to determine the rate order and the rate law for an overall reaction, many times when something is made up of multiple elementary steps, there's one step that's called the rate determining step. The rate determining step is the slowest step in the process. That's the one that's going to determine how quickly the reaction can proceed. If one step is slow and everything is fast, it's kind of like if you have an assembly line and there are multiple parts to your assembly line. Well, if there's one part of making your product that takes a really long time and everything else after that can be done quickly, then what's going to determine how quickly you can make your product is that slow part of your assembly line. It's much the same way for a reaction. The step that's the slowest is going to determine how quickly you can make your product. So for example, if we go back to our example where we have NO2 plus CO gives us NO plus CO2, the first step of this is the slow step. The second step proceeds quickly compared to the first step once this first step happens. So the rate law is actually going to be based on the first part of this, and carbon monoxide doesn't even appear in the rate law. If we look at another example here, we have three slow steps here. We have three steps. One of these is slow, the other two are fast. The fast step, however, is reversible, so it can go in either direction, but once we get into O2, this next process is slow. So if we write the rate law based on the slow step, the rate is going to be equal to K2 times N2O2 times H2. Now, when we write this rate law, if we go back to our slide here, you will notice that N2O2 does not appear in the overall reaction. We generally don't like to have things that aren't in the overall reaction in our rate laws. So what we're going to do is, N2O2 is an intermediate here. So if we look at N2O2, it's made in the first step. So the rate law for the forward reaction would be K1 times NO2 times NO squared. This is our rate for the forward reaction. So we can write a rate law for the reverse reaction, which is the rate constant. We write that as -1, since it's for the reverse reaction, is equal to N2O2. So since the rate is going to be the same going forward and backward, then we can set K1 times NO squared equal to K-1 times N2O2, which is this step here. And then we can rearrange this K1 over K-1 times NO squared. So we can just rearrange this to get what N2O2 is equal to, and then we can plug that in for N2O2. That gets rid of this intermediate showing up in our rate law. So how do we determine these reaction mechanisms? Well, the first thing we do is we determine a rate law by experiment. So this would be the rate law for the overall reaction. And then we devise the mechanism, and we predict a rate law given the mechanism. And then we look at the predicted rate law for the mechanism and the rate law that we came up by experiment. If they don't agree, we have to go back and try again. If they do agree, then we keep looking for additional supporting evidence, but we now have a proposed mechanism for our reaction. So we're going to stop here, and we will get some more practice with elementary rate laws in class. So I will see you in class.